Next, we take a look at two specific types of Riemann sums, a left-hand Riemann sum and a right-hand Riemann sum. Now the difference is basically a matter of where you choose your point on each subinterval to approximate the height of the function. So recall that a Riemann sum is basically a method for computing or estimating the area under the curve of the graph of a function. So if we have y is equal to f of x, what we do is we break up the x-axis from a to b into n subintervals. And then for each subinterval, we do an approximation of the area under the curve. So for example, draw some dashes to just show you where these subintervals range from. And then for each of these, we choose a point on the subinterval, evaluate the function at that point. This gives us the height of the rectangle, and then we multiply the height by the width, and the width is delta x, and we add them all together. Now for a left-hand Riemann sum, what we do is we always choose the point at the leftmost part of the subinterval. So for this first subinterval, I choose the point all the way on the left, and I evaluate f of x at this point, and then use that y value for the height of the rectangle. So my first rectangle looks like this. And then I continue. So for the second interval, I choose the point all the way on the left, evaluate the height, or evaluate the function at that point, and then use that as the height of the corresponding rectangle. And then for the next, I use the left endpoint like follows. Left endpoint, left endpoint, and the left endpoint. Right, so this would be a picture of the left-hand Riemann sum. And then the right-hand Riemann sum is the opposite. Instead of choosing the point on the subinterval all the way to the left, we choose the point all the way to the right. So for example, if I have, let's draw the same sort of graph, and let's divide it into a number of subintervals, just a couple, and let's draw where the subintervals slice the area. Now if I were to use a right-hand Riemann sum, instead of using the point on the left of the subinterval, I use the point all the way on the right. So I would take this x value, evaluate the function there, and then use that height to be the height of the rectangle for that little slice. So then the height would be here. And then for the next subinterval, I choose the point, the x value all the way to the right. So that's this one, evaluate f of x here. And I get something very similar. And for the next one, again, it's the point, the x value all the way to the right. So that would be this one. So I evaluate the height of the function here, multiply the height by the width. That gives me the area of that rectangle. And this one would be that point. And then for the final one, the rightmost point is over here. So it would look something like that. So that's an example of a right-hand Riemann sum. So in both cases, we're using a rectangle for each subinterval to approximate the area under the curve just over that individual subinterval. The left-hand Riemann sum, we choose the leftmost endpoint, and the right-hand Riemann sum, we choose the rightmost endpoint. Now, just a refresher of how the subintervals are divided. So if we have the x-axis, we have the point A and B, and A is also x0 and B is xn. So we have these points, these subintervals, notches. So recall that delta x is b minus a over n, right? If we have n pieces, and the total length is b minus a, right? The total length of this is just b minus a. If I divide that by n, I get the delta x for each subinterval. And then x sub I is given by a plus I times delta x. So x sub 0 is right here, x sub 1 we add delta x, x sub 2 we add delta x again, x sub 3 we add delta x again, and so forth. And then the ith interval runs over xi minus 1 to xi. Right, interval number 1 is between x0 and x1. Interval number 2 is between x1 and x2. So the ith one should be between xi minus 1 and xi. Right, so it always ends on the number of the interval. So this is important to keep in mind because the left endpoint is going to be xi minus 1 and the right endpoint is xi. So we're going to evaluate f of x either at xi minus 1 or at xi, depending on whether or not we're doing a left-hand or a right-hand Riemann sum. So for the left-hand Riemann sum, so I'll say left-hand Riemann sum with n subintervals, the formula will be the sum I equals 1 to n. So we do a sum over each of the n rectangles, and then we evaluate the function at the left endpoint. So the height of the rectangle will be f of xi minus 1, and then the width of the rectangle is delta x. So there's the formula for the left-hand Riemann sum. The right-hand Riemann sum, instead of evaluating the function at the left endpoint, we evaluate it at the right endpoint. So it's f of x sub I times delta x. So there's the left-hand Riemann sum, and here's the right-hand Riemann sum. Now if we want to actually see what this looks like, if we want to write out the terms of this series, I think that's a useful exercise. It adds a little bit of insight. So let me rewrite those formulas. So left-hand Riemann sum was the sum I equals 1 to n, f of xi minus 1 times delta x. And the right-hand Riemann sum with n subintervals is the sum I equals 1 to n, f of x sub I delta x. Now delta x and all the x sub i's, or the x sub I minus 1's, are determined based on n. So when you have a fixed interval from a to b, you divide it into n pieces. If you want to recompute this with a different number of subintervals, you'd have to start from scratch. You'd have to recompute your delta x, and you'd have to recompute where your xi are. Because if you have a different number of subdivisions, all of these numbers are going to change. So, but for a fixed number n, let's just take a look at what the terms look like. So if I plug in I is equal to 1, I minus 1, 1 minus 1 is 0, so I get f of x 0, and then times delta x. So the first term of the left-hand Riemann sum is f of x 0 times delta x, and then we plus, now I increment I to 2, so 2 minus 1 is 1, so I get f of x 1 times delta x, and then so forth, and the last one is when we reach n, so we have n minus 1, so it's plus f of x n minus 1 times delta x. Now the right-hand Riemann sum, on the other hand, we have x sub I. So when I is equal to 1, we get f of x1 times delta x. Then plus so forth, all the way up to f of x n minus 1 delta x, and then finally plus f of x n times delta x. Right, so this one stops at xn, where the left-hand stops at xn minus 1. Now this makes sense because if we think about x0 to xn, x1, x2, x3, x4, x5, and let's say n is equal to 6, so there's x6. The left-hand Riemann sum is going to use the following points: x0, x1, x2, x3, x4, and x5. Right, because x0 is the left endpoint of the first interval. x1 is the left endpoint of the second interval. x2 is the left endpoint of the third interval. x3 is the left endpoint of the fourth, the fifth, and the sixth. Now on the other hand, if we use the right endpoints, we're going to use x1, x2, x3, x4, x5, and x6. Because x1 is the right endpoint of the first interval, x2 is the right endpoint of the second interval, x3 is the right endpoint of the third interval, x4 is the right endpoint of the fourth, x5 is the right endpoint of the fifth, and x6 is the right endpoint of the sixth. So we use these 6 points for the left-hand Riemann sum when we compute f of x, I. We use these 6 points. And then for the right-hand Riemann sum, so I'll call that right-hand 6, and this one here, left-hand 6. We use these 6 points. Now notice that all of the internal notches are in common. So x1 is in common, x2 is in common, x3, x4, and x5. The right-hand sum has an extra one at x6, and the left-hand sum has an extra one at x0. So what would happen if we subtract these two sums from one another? So if we say the right-hand Riemann sum with n minus the left-hand Riemann sum with n. So notice that if we write this out again, f of xn times delta x is not in the left-hand Riemann sum. That corresponds to basically x6 down here. But the next to last one does cancel out here, and then they all cancel out. These guys cancel out, and then this one remains. So we have two that remain. So it's going to equal f of xn times delta x minus f of x0 times delta x. And you can also see that with this example with 6 subintervals. Right-hand Riemann sum has f evaluated at x6, but left-hand Riemann sum doesn't. These ones are in common, and then the left hand has one f evaluated at x0 where the right hand doesn't. So we get f of x6 minus f of x0 all times delta x. Now xn is always equal to b. So we get f of b minus f of a, and then all times delta x. Right? And x0 is always equal to a. So this is always the point A, and this is always the point B. So the difference between the right-hand Riemann sum and the left-hand Riemann sum is always given by the function at b minus the function of a times delta x. So f of b minus f of a times delta x. There's another property that is very important. So suppose I have a function that's increasing. So here we have a graph of a function f of x. And we have 2 points, a and b. And suppose that f is increasing. Now if we do the left-hand Riemann sum, we're going to use left endpoints to approximate our rectangles. So the approximate area is going to be the shaded area right here. So that's our left-hand Riemann sum with 4. Notice that the area that I shaded is less than the actual area under the curve. So we have the following result. If f is an increasing function, the left-hand Riemann sum will be less than or equal to the area under the curve. And the area under the curve will be less than or equal to the right-hand Riemann sum. So for that reason, we call the left-hand Riemann sum in this case an underestimate, and we call the right-hand Riemann sum an overestimate. Right? Overestimate means that it's greater than the actual value. Underestimate means it's less than the actual value. So if you have an increasing function, the left-hand Riemann sum comes up short when you're estimating the area, and the right-hand Riemann sum gives you too much. So if I use the right endpoints instead, I would get these triangles, or these rectangles. Right endpoint, and right endpoint. So notice with the right-hand Riemann sum, the area of the estimates are greater than the area under the curve. So for functions that are increasing, the left-hand Riemann sum always comes up short, the right-hand Riemann sum always comes up long. Now if you want to get a certain accuracy, you can use this formula that RHN minus LHN is equal to f of b minus f of a times delta x. So if you know what f of a is, and you know what f of b is, and you should because you're usually given the function f of x, you can figure out, and delta x, of course, is b minus a over n, so b and a are given. So you can use this to figure out how many subintervals you need so you can solve for n if you want the answer to be within a certain accuracy. So since the left hand and the right hand are basically underestimates and overestimates for the actual area, so you have, left hand Riemann sum, actual area, right-hand Riemann sum. And you can control the distance between the right-hand and the left-hand sum by controlling n. You can control how close your approximations are to the actual answer by using this formula to select the value of n. That is, as long as you have an increasing function. Now, if you have a decreasing function, it's just the opposite. So with a decreasing function, so here's a decreasing function. So if f is decreasing from a to b, then the right-hand Riemann sum is less than or equal to the true area, which is less than or equal to the left-hand Riemann sum. So if we look at our left-hand Riemann sum, we get an overestimate. So the rectangles, the area of the rectangles are always greater than the area under the curve. And then for the right-hand Riemann sum, we use the right endpoints, so we get an underestimate, just like that. So there's the right-hand Riemann sum with 4, and the left-hand Riemann sum with 4. So it's the opposite case. So if you have an increasing function, your left-hand Riemann sum is an underestimate, and the right-hand Riemann sum is an overestimate. If it's decreasing, it's the opposite. Right-hand Riemann sum is the overestimate, and left-hand is the underestimate. You can always remember this by just looking at a simple picture like this. Okay, if the function is decreasing and I use the left endpoints, oh, it's an overestimate, right? If it's decreasing and I use the right endpoints, it's going to be an underestimate. So you can always just do a quick picture to remind yourself of this. So that is the introduction to left-hand and right-hand Riemann sums.